Look into this. Heisenberg's uncertainty principle, it mainly emphasizes on the fact that it is difficult to measure the exact momentum of an electron or any small size particle, as well as the position of the electron accurately and simultaneously. Got it? So, which means if you try to figure out where exactly the electron present in an atom, we might mathematically try to figure out this is where it might be present, but in reality, when you try to check it out, it may not be at the same position as we expect. Okay, so in simple terms, we use this as it is impossible to measure simultaneously exact position and exact momentum. Okay, for particles as small as that of electron. Now, using this idea, Heisenberg was able to derive this factor that any change in the position, that means this is called as the uncertainty or the error. The uncertainty in the position, which is delta x, and uncertainty in the linear momentum, which is delta p. Got it? Okay. Both of them, right? Got it? Both of them are impossible to find out accurately and that too simultaneously. Got it? And he said that this product of the uncertainties always has to be greater than h by 4 pi. Okay, this is like the minimum amount of error that we will always encounter if you're trying to figure out the exact position and momentum of an electron or any small size particle. Got it? Why is this so? Okay, now look into this. If we figure out that there is an electron present somewhere, that information by the time it reaches you, the position of the electron will always change. Let me explain you in a simple terms here. Check out. Imagine if we have an nucleus here and around it we have different orbits. Okay. Practically, if you want to figure out where exactly is the electron present, what do? We usually try to figure out using a microscope, maybe. Okay. So let's say this is the microscope and our eye to check out where exactly electron is present. So imagine an electron is present here. This is what you're expecting, correct? But how do we know that electron is present here? We have to watch it, which means there should be some radiation that should come out after the reflection happening from the electron, isn't it? So which means imagine a light wave falling here. It is obstructing or maybe it is interacting with the electron, and then it is giving some radiations back, maybe by reflection. So if it happens, you will get an information that yes, electron is present here. This is the basic idea what we learn. Even for instance, how are you able to see me? The light is falling on me. Some part of the light is absorbed by my body, okay, and rest of the light is being reflected, and it is the reflected light which you are noticing. And based on that, you would be able to predict that where exactly, at what distance I'm sitting, what is the position, how my hand movements are, speed, everything you can determine. But what problem we encounter with electron? So there is one important aspect here. See, when the light is falling on me, that means the light is interacting with me, and as it start reflecting, my my position of the body is still at the same location. I'm not changing. The position of my body is not changing. Okay. Now that's one important aspect you need to understand about macro particles like us. When light interacts with macro particles, it interacts like wave, and wave will only give the energy, and some energy will be absorbed and some energy will be reflected. But the absorbed energy does not make me move. Just because I have absorbed some energy, will it change the position where I'm sitting? No. But that's not how exactly electrons work. If energy is falling on electron, electron will absorb some energy and it won't remain in the same orbit anymore. Okay, some part of the energy it will absorb, or maybe a particular type of wave it will absorb, and it will start jumping onto some new orbit. Now by the time that information reaches you that electron yahan par hai or electron is present in this orbit, that is the information which is reaching you. But by the time electron is not present at that location anymore, it is instead present at a new location. Correct? This is exactly what would happen. Kenneth, sorry, don't worry about writing the notes. This is a pre-notes. All of these notes would be given to you. Just keep a rough notes with you whenever there is a requirement for solving questions. That's it. Got it? Right. Check. So I hope you got an idea that electron does not remain on the same position as the information which we retrieve. The information what we are getting is different than what exactly the actual electron's presence is. Okay. Let me tell you another way of understanding this part. Imagine like this. You are here holding a camera and trying to take a picture of an bird maybe, which is moving from a particular position 1 to 2. So a bird is moving from here to here, correct? But what would happen here is when the bird is here, correct? Your camera will try to identify what is the speed with which it is moving, what is the distance at which it is present, and accordingly the shutter speed and accordingly the aperture will be adjusted. Okay, and then light is falling on it. So as the light moves back to you, I mean as the reflection comes to the camera, by this time the bird may have already moved to this position. So now the camera which is capturing the information of light is slightly confused, that am I getting the coordinates of this position, or am I getting the coordinates of this position, or somewhere in between position. So what does normally a camera does? It will take an optimization. That means it will take the information of this position, this position, this position, this position, all of that, and make a collage and try to give a better picture. But still, if you notice the old cameras, or if the shutter speed of the camera is not very good, you will see it like a blurred image. So even in the macro particles, identifying exact location of a particle or a substance of a body which is moving becomes slightly difficult. So in that case, could you imagine what might be the situation when it comes to electron? Electron, we are encountering two problems. One, it is moving extremely fast, so identifying its position becomes difficult. Second, when you try to figure out the here electron is present, by the time the electron might have already absorbed some energy and jumped to some new place. So this is a major problem that you encounter with electrons. So it is impossible to figure out exact position and exact momentum of a particle. Okay, so I hope you got an idea. So he came up with a concept called orbital. So he said, I could only discuss in terms of probability that electron might be present here or it might not be present here. And he figured out that in this situation, as per Bohr's model, if this is where electron is supposed to present, that is as per Bohr's model, we expect that the electron is present in an orbit, a specific location. But according to Heisenberg's uncertainty principle, he suggests that instead of assuming that it is present on a orbit, we can say it might be present anywhere in that region. And that region is what he termed as orbital. He termed that region as orbital. Got it? So in short, an orbital is a 3D space where the probability of finding electron is maximum. It is not exact where exactly the electron is present, but the probability of finding that is maximum. Okay. Now, to prove it into this perspective, how Heisenberg's uncertainty principle is correct, we will take 2 to 3 situations here. First situation, check out this. We can prove this. that electron can never be present inside the nucleus. We can prove this using Heisenberg's uncertainty principle. Let's look into that. According to uncertainty principle, right? If there is any amount of uncertainty in the position, any amount of uncertainty in the momentum, the minimum amount of product value should be h by 4 pi. Now listen up. Suppose if this is a nucleus and I can say the maximum uncertainty of the position of an electron could be anywhere between these 2 points, which is the diameter of that atom, isn't it? Which is 2r, diameter of that atom. Got it? So in that situation, we can say that 2r, which is the distance, which is the radius of the nucleus here, that could be your delta x. Okay. So this is the delta x, which is 2r. Okay. Or simply the diameter into delta p, which I can write as m into delta v. And that is greater than or equal to h by 4 pi. Got it? This is how much we know how the radius would be, isn't it? Now, what is the typical ratio? What is the typical radius or diameter of nucleus? As for Rutherford's model, we learned that it is approximately 10 raised to power of minus 15 meters. Okay, that is the radius. So if it is a diameter, it will be 2 times of it. So this much should be the radius here. This much should be the distance here. So therefore, I can say delta x is equal to 2 into 10 raised to power of minus 15. And what is the mass of an electron? It is 9.1 into 10 raised to power of minus 31 kgs. This is in meters, this is in kgs. Now assume this part, knowing these values, can we calculate what is delta V exactly? Delta V will be minimum error. What we can expect is h by 4 pi into 2 times of r, or h by 4 pi into delta x. Okay, into m, sorry, into m also, into m. So from there I can say delta V is equal to h, which is 6.625 into 10 raised to power of minus 34. Okay, this is the Planck's constant value. Okay, those who are not aware, do not worry about it. It's just a constant value. Correct? So that into 4 pi 3.14 into delta x, which is 2 times of 10 raised to power of minus 15, into mass, which is 9.1 into 10 raised to power of minus 31. Got it? So if I put all of these values, right, how much we will get approximately? This value I'm getting is approximately 5 into 10 raised to power of 10 meters per second. Okay. Have you noticed this value? Isn't this absurd? Because speed of light itself is going at a speed of 3 into 10 raised to power of 8 meters per second. While what we are expecting is the uncertainty in the speed. Uncertainty in the speed of electron is overcrossing that value 5 into 10 raised to power of 10 meters per second, which is impossible. Okay, uncertainty is like an error. An error cannot be this big, that is it is overshooting the value of the speed of light itself. Because if any particle is moving with the speed of light, it cannot be defined as, I mean, it cannot have any mass anymore. So definitely this is absurd, and this clearly suggests that electron can never be present inside the nucleus. Okay, so that's a simple way of defining that this kind of possibility, this kind of value is impossible. Okay, so another way, look at this one. If I can say as a note that if you are trying to define the accuracy of an electron, that means you are expecting that the delta x is 0, or you're trying to figure out that, well, I'm able to find out the electron's position accurately. In that case, you know that delta V, which is inversely proportional to, or if you notice the formula here, that is h by 4 pi m into delta x. So that will be equal to infinity. It is undefined here, correct? So that means we can never be clear about what is the speed of the electron. Got it? So both of them will always uh, intervene with each other. Got it? If one increases, the other decreases, and so on. Got it? Another logic, imagine like this. Okay, simple term. A lot of time, students only ask me, sir, why don't we think this way, that we are trying to figure out electron accurately by sending a particle, by sending the light, which has a very, very small amount of wavelength. Yes, agreed. Let's say we have small wavelength. And you know that if the wavelength is smaller, the frequency is higher. And frequency is higher, you're sending a high energy radiation. Okay. In that case, while you're trying to watch the electron, you know, where exactly it is present, now there are two problems. Correct? Now, if it goes here, imagine this, I'm just zooming in. This part I'm zooming in. This is where the electron is. And let's say this is the line of sight where the light is coming. So if we are sending a wavelength which is very short, correct? Then the chances that the margin of error will decrease. Only this much is the delta x value. You can see a very small amount is the delta x value here. So that means you are trying to figure out almost very accurately. But the minute the electron interacts with this light, what would happen? It will not stay in this orbit anymore. It will get into some higher orbit. It will immediately jump into some higher orbit. Okay. So now the electron would be somewhere at the higher orbit here. Got it? So you are trying to figure out the accuracy on the position, then you will not be able to clearly identify what is the speed at which the electron is moving. Okay. Second, suppose if I try to minimize that. So, okay, now you are thinking, okay, may not be identifying the exact position. Instead, I'm trying to figure out that electron has to be always in that same orbit. So I'm sending a lower energy radiation. If you're sending a lower energy radiation, that means the wavelength will be longer. So now what would happen if you take a longer wavelength here like this, okay? The chances that the electron, you know, chances that the wave interacting with electron minimizes, and that increases the delta x value. So that is the chance that the radiation will actually make an interaction with electron is very less. Clear? So again, you are trying to increase the delta x value. So if you try to increase the energy of the radiation, delta x may be less, but delta v is completely uncertain. But if you decrease the energy, delta v might be correct, but delta x is uncertain. Okay, so that's the biggest pickle that you will notice here, and that's what Heisenberg is trying to uh, refer it to. All right, that why we have this problem. Now notice, if the similar thing is been asked for some kind of, a macro particle like cricket ball. Okay, so if you have an uncertainty of position of a cricket ball which has mass of 100 grams and moving with a speed of 10 plus or minus 2, plus or minus 2 meters means this is the variation which you are expecting. Got it? So in that case, how do we figure out what is the uncertainty here? Please look into it. Okay. So here uncertainty will be that there is a uncertainty in the speed up to 2 units, 2 meters per second. Got it? And the mass is 100 grams, which is around 0.1 kg. Got it? So delta x dot delta p is equal to h by 4 pi, which implies delta x dot m into delta v is equal to h by 4 pi. Correct? So I'm trying to figure out what is the uncertainty in the position of the cricket ball. So that is h by 4 pi m into delta v. So that makes it 6.625 into 10 raised to power of minus 34 divided by 4 pi, that is into 3.14, into mass is given as 0.1, into delta V, which is 2. Okay. Solving all of that, I'm getting approximately 2.5 into 10 raised to power of minus 34 meters. Can you imagine minus 34 meters? I mean, this is hardly anything, right? Which suggests that there is hardly anything which you can notice where there is an error or there is an uncertainty in the position. Hence, we can say Heisenberg's uncertainty principle is only valid for microscopic particles like electrons moving with high speeds, while it is not applicable much for macro particles. Everybody understood this logic? Got it? If anybody has any doubt in this case, please do ask me now. You can please check once again. If there is anything you wanted to discuss, please ask me now. All good? Can we go ahead? Now, right. Samira, Kenneth, please check this beta. Last time we discussed one thing, that there is a hypothesis, de Broglie's hypothesis, which suggests that a particle can always show both wave and particle behavior. Okay. Any body, any rigid body can always show both particle behavior as well as wave behavior. Okay. But the microscopic particles will have better application of de Broglie's hypothesis. And according to de Broglie's hypothesis, the wavelength associated with the moving particle can always be represented as h by mv. Okay, so lambda dB means de Broglie's wavelength is h by m is the mass of the particle, v is the speed of the particle with which it is moving. Got it? This is just to give you a briefing on what we discussed in the last class. This will be useful here going ahead. So first, let me give you one more Heisenberg's uncertainty principle case, and then how this de Broglie's hypothesis is useful along with Heisenberg's uncertainty principle. We'll check. Okay. So do a very similar question as what we did earlier here. Think about a golf ball, got it, of mass 40 grams, moving at a speed of moving at a speed of 45 meters per second. Okay. If speed can be measured within accuracy of 2%. Okay, then calculate uncertainty of its position. It's not a difficult one, very similar question as that of the cricket ball question. So please check. All we need to do is just substitute that part here. values and just get delta x. Before that, notice one thing. Instead of giving the accuracy in terms of the exact value, I gave you in terms of percentage, which means delta V will be equal to 2 percentage, 2 by delta X into 45. That is the change. And which comes to be approximately 0.9 meters per second. So this is the value of delta V. And since we know the delta X value will be equal to H by 4 pi m into delta V. So that is equal to 6.625 into 10 raised to minus 34, which is the Planck's constant. That into 4 into pi. Pi, I can write it as 3.14 into mass 9.1 into 10 raised to power of minus 31. Sorry, mass is 0.041. Okay, let me back immediately. Sorry, 0.04 kgs. That into delta V. Delta V is 0.9. Okay. Substitute all of these values. I am getting approximately 1.46 into 10 raised to power of minus 33 meters. So again, you can notice that this is a very absurd value, right? This is an extremely small value, which means you are able to identify the position accurately. Got it? Now
Uh,
notice another
uh,
important
sir,
application. Yes, beta.
sir, is it still the exact value of it?
Which one?
Exact position of the this one, the
Yes, yes.
1.46 into.
Yes, beta. This is almost like exact position only, right? Got it?
Okay, sir.
Hmm. That's the reason why we are saying that Heisenberg's theory is more validated for microscopic particles. Got it? So for
Uh,
macroscopic particles, no matter even imagine even if it is moving with 100 meters per second, 300 meters per second, still we'll be able to say it. Got it? Let's say there is
got
a
it.
maglev which is moving on, uh, Japanese rails, right? I mean Japanese rail tracks, correct? It might be moving with, let's say, approximately 600 meters per second. Still, standing up there, right? If you are able to notice that where exactly it is, it might rush in front of you quickly, okay? But where it will be after some time, your calculation and its value will always match, isn't it?
Uh, yes, sir.
So, which means it is showcasing that. But according to Heisenberg's uncertainty principle, that will never match for electron. For electron, it will never match. You might expect, based on your classical calculation, that means classical physical calculations, you might expect ki electron is moving with some v velocity and in this particular track, and you are expecting electron should reach at this position, but it may never make it there. Got it?
Got it, sir.
Why? Because we don't know after the interaction with light, it will change its trajectory only. Okay. So then
Yes, sir.
we are waiting in one trajectory, but electron is in some other trajectory altogether. Hmm? Right.
Yes, sir.
That's a problem. Okay. And great part of this theory is this becomes the basis of quantum mechanics. Got it? And going ahead, when you do the research in your future, you will realize that, okay, how quantum mechanics is completely changing the idea of, perception of particles present at a particular point. Okay.
Okay,
Done?
sir.
Right. Now, see, another important case is you have to relate uncertainty, uncertainty in de Broglie's, de Broglie's wavelength of an electron. Okay, given given linear momentum, linear momentum in a particular orbit. Okay, So how do we do this one now? Please check. Okay. You know that formula wise delta x dot delta p is equal to h by 4 pi. Okay. This type of questions are mainly focused for advanced, correct? Because here the thought process should be very different, that you should know how to use the integrations, I mean differentiation to your application. Check. You know that lambda of de Broglie's is equal to h by p, correct? So now differentiate that. So we'll get d lambda is equal to minus h by p square into d lambda, correct? Take a mod of it. So we'll get this as d lambda is equal to mod of h by p square minus into, sorry, dp here. My mistake, it is dp into dp, correct? Which means, which means this can be expanded to the fact that if there is any uncertainty in the de Broglie's wavelength, it can always be written as h by p square into uncertainty in the momentum. Now, this is a logic that you can use it here directly. So, what do we get here now? So, I'll get this as delta x dot delta p can be written as p square by h into delta lambda is equal to h by 4 pi. That's the application I'm talking about. So, now you know that delta lambda is equal to h by 4 pi. This becomes square and p square into delta x. Please check. This is the way you can identify the uncertainty in the de Broglie's wavelength. Okay, given the momentum of the electron or momentum of the body is given, in that case you can use this formula. Okay, I'll change slightly here. What if we'll change the question. If lambda dB is given, lambda dB is given, and need to find, correct, delta lambda dB. How much is the uncertainty in the wave? That means there is some value given, but we need to figure out how much is that uncertainty. In such case, what do we do? Same formula. See, look into it. Lambda, got it? 1 second. Okay. See, lambda is equal to h by p. Again, I'll differentiate this time. But this time, what I'll do, I'll put p here and h by lambda here and then differentiate. Now, this time when you differentiate, you'll get this as dp is equal to minus h by lambda square into d lambda. And the mod of that will be delta of p will be equal to, h by lambda square into delta lambda. Substitute this value back into the equation. What do I get? Delta x dot delta p. Now delta p, I'm writing it as h by lambda square into d lambda. That is equal to h by 4 pi. Okay. Now you can clearly notice that h can be cancelled off. So we will get this as delta lambda is equal to lambda square by 4 pi into delta x. So you can see, depending upon how the question is given, accordingly you can modify the equation. Okay. If the lambda is given, you will use this equation. Okay. What if you know that kinetic energy, another important note, that is kinetic energy of any particle will be equal to half mv square. If I multiply 2 on both sides and m on both sides, I'll get this as 2m kinetic energy, which is equal to mv whole square. Mv whole square is nothing but p square. Correct. So now what I can do, that lambda is equal to h by p. What if I square it on both sides? Lambda square is equal to h square by p square. Now p square, I can replace that with 2mke. Correct? This is what I'll get. Okay. Now differentiate this once again. what do we get in terms of, if you want to get in terms of kinetic energy and lambda, what will I get here? So I can get this as 2 lambda into d lambda on differentiating. That will be equal to h square by 2m with minus by kinetic energy square into d of kinetic energy. Correct? This is the differentiation. Correct? So again, lambda can be represented back as, this same value here, right? So I can take that lambda value to the other side. So I can get it as d lambda is equal to minus h square divided by, okay, 2m into kinetic energy whole square, that into lambda. And lambda now can be written as into, sorry, this into d of kinetic energy. Correct? So that can be written as minus h square minus h square divided by 2m into kinetic energy square into lambda. Now lambda can be written as h by under root of 2m into kinetic energy, that into d of kinetic energy. So d of kinetic energy. So you can see now in the same equations, when you want to get delta lambda in terms of kinetic energies, uncertainty, just use this and substitute in this formula. That's it. Or use this, substitute in this formula here, or earlier formula what we derived. Okay. So this is the way we can play around with, Heisenberg's uncertainty principle. Whatever data that is given, whatever equation that is being asked, you can always play around. Got it? I'm just giving a briefing of few cases, how we can write it in terms of de Broglie's wavelength. Okay. The common one, which has been usually asked in JEE mains as well as advanced, other than the original form, is this one. Okay. Let me write on that other form also. Okay. Common form, common form. 1 second. Sorry. The other common form, you can see how we can derive that. You know that this is x into momentum p is somehow related to h by 4 pi, correct? Right. Of course, it is not exactly equal to, but somehow related to it. So I can write it as proportion, correct? Now think about this one. What if you know that, how do we define force? Okay. Force is equal to rate of change of momentum. Okay. So that means momentum, something like a momentum per time. This is the value you should get. So this is proportional to. So force is proportional to momentum per time. Got it? And now, what if I multiply that with some factor like x? So this is like energy. Okay. That is energy. So that multiplied will be proportional to P by T into x. Now, if I take this force into distance, if you remember, force into distance is always work, and work is energy. So therefore, I can write this in terms of energy multiplied by time is proportional to linear momentum multiplied by x. And can you notice that linear momentum multiplied by x will be proportional to h by 4 pi. So that's the reason why we can write this formula as well. That is delta x dot delta p. If this is greater than or equal to h by 4 pi, the same logic can be applied even when you have delta E into delta T. That will also be greater than or equal to h by 4 pi. Clear now? So in any form that is the question asked, whether this information or the energies information given, times information given, you can always use this part. Okay. I hope this part is clear, everybody. Any doubt in the first three cases, or I mean, the last three cases which we discussed, please let me know. Doubt, everybody. Any issue here?
So can you explain the part where you got the value for k square?
Perfect. Check. What I'm saying, whenever you have something like a sine kx, correct? Sine kx is the behavior of a wave, right? Sine function is a behavior of a wave, correct? Sine wave कैसा होता है बेटा ऐसे ना, right? So it is a behavior of a wave. That means when a particle is moving like a wave, that is the behavior, correct? And the value of k in that is 2 pi by lambda. That is how much amount of wavelength it is making. Clear? So wavelength is up to this part. This is lambda. Understood? And how do we get to know the lambda of a particular lambda of a particular particle which is acting like a wave? That's what is exactly de Broglie's wavelength, right?
Right.
So therefore, de Broglie's wavelength को कैसे define किया बच्चा हमने? That is h by p, है ना? H by p, p is linear momentum, and that is h by p can be written as m into v. अगर मैंने स्क्वेयर किया इसको लैम्डा स्क्वेयर, देन इट विल बिकम एच स्क्वेयर बाय पी स्क्वेयर. और पी स्क्वेयर का वैल्यू क्या है बेटा? पी स्क्वेयर कैन बी रिटन एज 2m into kinetic energy. So that is the value which I've used here back. Do you have any doubt now?
No, sir, clear.
Right. Others, see, if you understand this, you will enjoy rest of the part of the quantum mechanics, how to draw the graphs, everything that is related to it. Got it? So if you still have any issue, please do ask me right away. Okay. Kenneth, is this clear, beta?
Yes, sir.
Right. Samira, how about you?
Yeah, again a little bit.
Great. Okay. Okay. Now let's see the fact. Where are these quantum numbers exactly useful? Okay. I told you what is the significance of quantum numbers, right? But where is it useful? Okay. And how do we incorporate that with our structure of atom? Listen to it. The first three quantum numbers are straight away derived from Schrodinger's equation. Okay. The first of the quantum number is represented as n, and that is called principal quantum number. Okay, what does that signify? Well, its essence is to figure out orbit number related to Bohr's model. Let me remind you about Bohr's model. Bohr's model simply suggests that electron always moves across the nucleus in a concentric circles at a fixed distance. And starting from the first orbit, we give designation as 1, 2, 3, 4, and so on. So that n value actually represent the quantum number, sorry, the n value represent the orbit numbers of the Bohr's model. Got it? So therefore, when we write n is equal to 1, n is equal to 2, n is equal to 3, we are in fact agreeing upon the Bohr's model's orbit distance. That is, okay, electron might be present at this distance or this distance or this distance or this distance and so on. Okay. Or at least we are talking about that region. When I'm talking n is equal to 3, that means I'm talking about this region probably. Got it? So the n represent the value of the orbit number. Second, it also signifies the size of the atom. Of course, if n is larger, we can say the size of the atom is more, right? And lastly, what is the distance away from nucleus? Got it? That's the main factor we need to check. 1 second. 1 second. Sorry guys, check. So the n value also suggests us how far the electrons behavior, or how far the electrons behavior we are discussing, we need to check, right? So that is distance away from the nucleus. This is the kind of information we will fetch from the first quantum number, which is called as the principal quantum number. The second quantum number, known as the azimuthal quantum number, it mainly emphasizes on the shape of the subshells. Now, here is a very important catch, that wherever there are any orbits defined, like in atom, there are orbits defined, orbits as in the space, the boundaries in which some electron might be present, those boundary lines. If within those boundaries, electron might be present in that space, making some kind of a shape. Got it? That means, is the electron moving in a particular shape? No. That means electron's presence itself will create a shape, like a cloud, for instance. You know that the clouds in the sky always have various shapes, right? Like that. Does that mean a cloud does not mean a big lump of solid, or a rigid body there, right? A cloud is a mere representation of droplets of water. Simple. Those are just droplets of water, isn't it? Of course, mixed with air. In a similar way, electrons' presence is creating some kind of a cloud within that region, okay, within that boundary. That's what is representing azimuthal quantum number. The azimuthal quantum number emphasizes that how many various shapes you can get in a designated space. Okay, so that shape of the subshells is what represents azimuthal quantum number. Every shape is designated with an alphabet, or a label with an alphabet, starting with S, P, D, F, G, H, A, I, and so on. Okay, starting with S, P, D, F. So remember, these are the names. And what does that represent? S means a spherical cloud within the designated boundaries. Within that boundary, I'm able to see some spherical cloud. And that spherical cloud is designated with a value in the Schrodinger's equation as 0, when L is 0. Got it? And if L is 1 in the Schrodinger's equation, that represents that the electron cloud is appearing like a dumbbell. Okay? If L is equal to 2 in the Schrodinger's equation, the coefficient is 2 in the Schrodinger's equation. That means it is designating the double dumbbell shape. Okay? I hope all of you understood this part. So notice, for example, n is equal to 3 is a boundary line, because principal quantum number defines the boundaries of, or the spherical shape or shells, correct? Numbers. So if n is equal to 3, then within 3, you'll actually identify three different shapes. One is a spherical shape, which is like this, a cloud which is spherical. You'll see another cloud which is a dumbbell like this. This is that dumbbell. Okay. And then third cloud, which is like a double dumbbell. This one. This is like a double dumbbell. These are all combined, by the way. This is how it combined it looks like. So this is a double dumbbell. So within that third shell, we are noticing three different shapes. That identifies as a pattern. And what is the pattern we notice? That for every n value, there would be same number of L values. That means same number of L values represent same number of shapes. That is, if n is equal to 1, L value will be 0. That means it will have only one shape, and that is spherical. Correct? And that spherical labeling we write it as 1s. If n is equal to 2, then we can have two different values. L is equal to 0 also, and L is equal to 1. 2 means also spherical, and that spherical we represent it as 2s. And L is equal to, sorry, L is equal to 1 here. L is equal to 1 represent that it is dumbbell. Okay, and that is labeled as 2p. So 2p is the shape of that cloud. And these shapes designated are called as subshells. So this is 1s subshell. This is 2p subshell. Okay, this is 2s subshell. So can you identify something that if n is equal to n, there is one subshell. If n is equal to 2, there are two subshells. N is equal to 3, we should have three subshells and so on. So if n is equal to 3, correct? So we'll have three different shapes here. So that includes L is equal to 0, which you write it as 3s, L is equal to 1, which you write it as 3p, L is equal to 2, we label this as 3d. Okay. I hope that is clear, everybody. So azimuthal quantum numbers purpose is to figure out what is the shape of that cloud within the orbit. And we call those shapes as subshells. Okay. Now, next quantum number is even more interesting. Electron, when it is forming a cloud, right, it will try to use as much space as possible within that limitations of the boundaries, correct? If let's say n is equal to 3 is quite big here, like a size of a football, let's say. Okay, 1 second. Sorry. So if what I was saying is that if there is a designated space like a football, right, that is the space maximum. In that, electron has to use as much space so that it can accommodate more number of electrons into that space, right? What will it do? First, we will assess the cloud. What kind of clouds it can make? Okay, let's say one cloud we notice that it is spherical like this, a hollow sphere kind of thing. The other one we found is like it can make some kind of a dumbbell like this. Okay. The other cloud we found is like it is more sharper like this, but that is called double dumbbell like this. These are the shapes we found. Correct. Now, of course, we have to cover as much space as possible. Within that shape, we try to cover as much space where electron can be accommodated. So what it happens is, if it is a spherical case, no matter wherever you move in the three dimension, it looks exactly same, and its density around across every direction will be same, which means it cannot have any specific orientation. Okay, but when it comes to dumbbell shape, you can notice that if there is a three dimension here like this in three-dimensional space here, if a dumbbell is given in this direction, correct, one can be in this direction. One dumbbell without intervening the other dumbbell, I can place it here. One dumbbell, I can place it here like this. Okay. So you can see these dumbbells can be placed in x-axis, y-axis, and z-axis. How many dumbbells I can place? Three different dumbbells, isn't it? Which means to accommodate more number of electrons, now the orientation is helping. So that means depending upon the shape, we can have a certain number of orientations we can make. Got it? And this, how many different orientations we can make is what is designated from magnetic quantum number, right? So magnetic quantum number is suggesting that for a different shape, how many orientations can be associated. Okay. So number of orientations will always depend upon the L value again. That will be equal to 2L plus 1 value. That is, if L is equal to 0, if L is equal to 0, ML values will be how many? Okay, ML values. How many values we will get? Only one value we will get. That means only single orientation. Single orientation is a way to say that it is only spherical. So it's very spherical sphere. Wherever you rotate, it will always have the same type of orientation. Okay, that means the shape does not change, the density does not change, it will remain the same. But if L is equal to 1, how many ml values I will get? Ml values I'll get is 3, correct? That means I can have 3 different orientations, correct? And the same p orbital, now I write it as px, py, and pz. When I write it as p, it is subshell. But when I write it as px, py, and pz, that means I have assigned its orientation also. I have assigned its direction also. And once you assign the direction, then we call them as orbitals. Now these becomes orbitals. So magnetic quantum number is giving us the information of orbitals, that how many orbitals we can have, how many orientations we can have. So this is one orbital, this is one orbital, and this is another orbital. So in short, if it comes to S subshell, we can have only one orientation, one orbital. Okay, the subshell itself is an orbital. But when it comes to P can have Px, Py, Pz. 3 different orientations. That means 3 different orbitals it can have. Again, let me remind you what is orbital, everybody. We discussed in the start of the class. Orbital is a space in which finding of electron is maximum. Probability of finding of electron is maximum. Okay, or up to 95%. That space is what we call it as orbital. Okay. Next, if L is equal to 2, the ml values we will get here are 5. Okay. Now this is based upon calculations, mathematical calculation in the Schrodinger's equation. The names are dx square minus y square. The orientation directions, the directions are represented as dx square minus y square, dz square, dxy, dyz, and dxz. So how many orientations? 5 different orientations, and these are their respective labelings. Okay, so that means we have 5 different orbitals. So if I write down that if L is equal to n, if L is equal to some L value, then number of orbitals present in that shell, in that particular shell, will be equal to how much? 2L plus 1. These many number of orbitals we have. Okay. Now listen up. Because our idea of Schrodinger's equation is all about discussing their coefficients, right? So here also, every orbital should be designated with a value. We know that there are 5 orbitals, but what are the values of each orbital? To find out what is the exact value of each orbital is represented by minus m by ml, which is equal to minus L to plus L values, minus L to plus L, which means, see, if L is equal to 0, then ml value is 1 and only one orientation. So, and minus 0 to plus 0 means only 0 value, right? So the value of that is 0. While L is equal to 0, ml number of values are 3. And what are those exact values? Sorry, L is equal to 1. Then that is minus 1, 0, and plus 1. So usually this is Px, Py, and Pz. Conventionally, okay, Pz is always assigned towards 0. Okay. So next, L is equal to 2, then ml values are 5. It starts from minus 2, minus 1, 0, plus 1, and plus 2. That is dx square minus y square, dxy, dyz, dxz, and this is always assigned towards dz square. So z is conventionally always assigned towards 0, whether it is in the form of pz or in the form of dz square. Okay. Rest of them are interchangeable. I can make dxy here and yz here. That is not going to make any difference. I can put dz square minus y square here or here, or I can exchange these two. There is no problem. Only one thing conventionally what we follow is dz square and pz. They are always assigned towards these values. Clear, everybody? These are the values that we will assign. Okay. So now what we can say, the total number of orbitals present in the n values is how many? Let me show you with an example. Suppose if you have n is equal to 2. For n is equal to 2, the L values are 0 and 1, correct? And we call those subshells as 2s and 2p. These are the subshells. Then what will be the ML values? For 0, we'll have only one value, 0, and that is also called as 2s. And for 2p, we will have three values. What are those three values? -1, 0, and +1. And that includes 2px, 2pz, and 2py. Okay. And this is very interesting. These are total number of orbitals. Please notice something. If n is equal to 2, then how many orbitals I'm getting, everybody? Total orbitals are 4. That means within that region, how many orbitals I will have? 4 different orbitals. So for n is equal to 2, if it is 4, if n is equal to n, how much we will have? N square. So therefore, number of orbitals will be n square in this case. Clear on that? One second. Finished? So similarly, each orbital maximum carries 2 electrons only. Whenever we have an orbital, maximum number of electrons it carries is only 2. If that is the number of electrons carried, then what is the total number of electrons present in the shell? Because n square is the number of orbitals and two electrons are present in each orbital. So the total number of electrons present will be 2n square. So this is the information you should learn. Got it? So for every different quantum numbers, how are those values designated? Clear? I hope all of you understood this logic. So these three quantum numbers are very, very important, everybody. So one is principal quantum number, azimuthal quantum number, and magnetic quantum number. In short, let me summarize. Principal quantum number is telling us which orbit you are talking about. First orbit, second orbit, third orbit. Azimuthal quantum number is telling us about which shape of clouds that electron is making, right? Which we call it as subshells. Third, how many number of orbitals, how many orientations of those clouds we can have. That is being discussed by ML values. And each orbital will have maximum of 2 electrons it can carry. So you can calculate the number of electrons as 2n square. That's all good, everybody? Here? Right. So this is how much you need to learn from Schrodinger's equation. Okay.